Let's take a look at angles, degrees, and arcs. And let's discuss some basic definitions. Of course, you remember from algebra, this is a line. So it has arrows on both sides, so it goes forever in both directions. Now, when you just go from a point and then you go forever in this direction, this changes. It's no longer a line. This is called a ray, sometimes called a half line. Now, this right here is our initial point, and then we can create an angle by rotating this ray. For example, let me draw this. Now this right here is our initial side. Now we're going to keep that initial side, but we'll make a copy of it and then we'll rotate it. So we'll rotate it up like this. While this is our initial side, this is our terminal side. So that's our terminal side. And this angle is formed right here. We'll put as theta. Oftentimes these angles are represented by Greek letters. They don't necessarily have to, but you see theta quite a bit. In some books you'll find where they'll put an uppercase letter here, like uppercase A or uppercase B, and so forth. This point right here is referred to as our vertex. Now in various problems you may see them refer to the terminal side, initial side occasionally, vertex every once in a while. Some of these definitions are more important than the others. Ray, you probably won't see that that definition used a lot, but you'll see terminal side referred to. This again forms an angle. Now as we go, here's our initial side, and as we go counterclockwise, our angle is going to be positive. If we have, here's our initial side, and then here's our terminal side, and I'm going clockwise. Well, if you're going clockwise, then your angle is going to be negative. Important to keep that in mind when you're going through and working problems, because if you go in this direction, then it'll be negative. But on the other hand, if I were to put a start here and go around over here, this red angle would be positive. You notice that they both give us the same terminal side. We're going to see that there's many different possibilities that would give us the same terminal side. We can go this direction, we go this direction, you could go this direction and then all the way around and back to that side. There's actually an infinite number of possibilities that would give us this terminal side. Now where they have the same terminal side, that's referred to as coterminal. So for example, if you have two angles that give you the same terminal side, refer to them as coterminal. So same terminal side. Now if we start at our initial side, and oftentimes this is put on a XY coordinate system, but we'll talk about that later on. If I go halfway over, for like a straight line, you go halfway to right here. draw it very well. This is 90 degrees. If I start here and I go all the way over in terms of a line over to that would be 180 degrees. If I have my initial side here and I'm going to go this far, this is going to be, by the way, I'm adding 90 degrees, so this would be 90 plus another 90 is 180 plus another 90 is going to give us 270 degrees. And if I go all the way around, so here's my initial side, and I go all the way around, and my terminal side falls on my initial side. This would be 360 degrees. So we've done one complete revolution around. Now I could keep on going. I could go around again, and that would add another 360 degrees on it. So it would be 720 degrees. And it would be coterminal because they have the same terminal side. And even more than that, they have the same initial side also. Okay. Now we've talked about those a little bit. There's a breakdown that you can come up with that is demonstrated by this first problem. So let's take a look at this. Find number of degrees in an angle formed by rotating the terminal side counterclockwise through the indicated fraction of a revolution. Okay, so let's take a look at our first problem in the first part, which is 1/2. Yeah, we've talked about this already. Starting here, and now when they say find the number of degrees in an angle formed by rotating the terminal counterclockwise to the indicated fraction of a revolution. This train blowing, so let me pause this. Okay, I believe the train has stopped. I live near the train tracks, so sometimes that train starts blowing, and so we're looking at 1/2. Remember how I said we've already looked at this one? 1/2 of a revolution, all the way around is the full revolution. So 1/2 would go over to right here. And the instructions are asking us to find a number of degrees. Well, we already said that over to there is 180 degrees. That one is pretty easy. You could just visually see it. But, like 3/4. If I start here, and 1/2 is over to here. 1/2 is like 2/4. So 3/4 would be right here. I sometimes forget to put those arrows on there, but that would be 3/4 the way over. And we've already said that that's 270 degrees. Okay, well, still fairly easy to see, though we'll talk about different other ways of doing those. 1/5. Oops, scroll down a little bit. Yeah, this isn't so easy to see. One full revolution is 5/5. So we think about splitting this this entire circle here. Let's imagine a circle here. And you think about splitting that into fifths. You know, here, 1/2, that's easy. You can split it in 1/2. 3/4, you can split this into quarters, and then you get your 3/4 there. But 1/5, I'm going to try to eyeball this. Probably not going to be very good at it. Let's say that's 1, 2, 3, okay, 4, 5. So 1, 2, 3, 4, 5. The idea is each one of these little segments is the same angle-wise, Obviously, this one looks a little bit bigger. So 1/5 would be approximately right over to there. Well, what in the world would that degree be? Well, let's go back up to the 1/2. All the way around, back to our initial side, would be 360 degrees. So when we say 1/2 of revolution, we're saying 1/2 of 360 degrees. So we're taking 1/2 times 360, which would give us our 180. Over here, when we said 3/4 of a revolution, we're saying 3/4 of 360 degrees. And 4 and 360, both divisible by 4, that gives us 90 here, which gives us our 270 degrees. So this one is not so easy to see. 1/5 of revolution, we can simply just take 1/5 times 360 degrees. And kind of early, but let me see if I can do some basic math in my head. 35 and 72 degrees. Let's see, 735. I just let it blow. It's train again. Okay, so 180 degrees, 270 degrees, and 72 degrees. The graphical way to view it, it works pretty good when you're dealing with 1/2, 3/4, and so forth. But if you got something like 1/5, not so easy to see. Well, let's take a look at 4/5. And I could use these same segments here, each one of these being 1/5. So 4/5 would be right about right here. So what we're looking at graphically, there's our initial side, and then this is about 4/5 the way over. So that's what we're trying to find. Sometimes that's handy just to come up with a rough sketch so that you can compare the answer you got with what it should be graphically. And that'll kind of tell you if you're close or if you messed up. I see it's greater than 270 degrees but less than 360. Well, we're going to take 4/5 of revolution, so we'll take 4/5 times 360 degrees. And let's see. So 5 and 360 both divisible by 5. 5 divided by 5 is 1. 360 divided by 5 gives us 72. Okay, so then 4 times 72 gives us 288 degrees. Now, just since I did wake up kind of early this morning, let me double check that. 4/5 times 360. So 4/5 times 360 degrees does give us 288. So that would be your answer for that one. Now let me go ahead and save this page. And 01.pdf. Okay, there we go. Now our next problem is says find the fraction of a counterclockwise revolution will form an angle with the indicated number of degrees. So we're starting out with the degrees and we want to know this fraction right here. So we're going in reverse. Okay. So let's take a look at this problem. We got 90 degrees. And I'll start off graphically first. Here's our initial side. 90 degrees, we've already said, is up to here. Okay, one revolution is completely around back to our initial side. That'd be 360 degrees. So going this way, 90 degrees, looks like it's a quarter of the way, because if I were to draw it, 360 degrees would be over to there. And you see if I were to draw these, extending those out, there's a quarter, 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 so split up into fourths. So our answer for this one would be 1/4 of a revolution. Then we got 20 degrees. Okay, 20 degrees. That's not as easy to see. This is falls perfectly on this angle right here. It forms 90 degrees. So that one's a lot easier to see. Now, let's think about how we could do this without the picture. I'm trying to change this to number of revolutions. 360 degrees all the way around would be one revolution. 180 would be half a revolution. So I think, what kind of connection is there between 180 and 360? Well, if I create a fraction, 180 over 360, I'd give it to me. So for this one, if I were to take my 90 degrees divided by 360 degrees, the degrees would cancel, these zeros would cancel, and I'd get 9 over 36, which gives me 1 over 4. So on these one, to go from the degrees to the number of revolutions, you just simply divide by 360. I could draw this if I wanted, and I'll do it just to give us, again, a general feel of where does 20 degrees fall. Now, right here is 90 degrees. Halfway up there is 45 degrees. So 20 would be somewhere right here. Don't know exactly where, but that would be roughly 20 degrees. Okay, I said we're just going to divide by 360. So we'll take our 20 degrees, divide by 360 degrees. Degree marks cancel, zeros cancel. We got 2 over 36, which gives us 1 over 18. So 1/18 of a revolution is what that's equal to. Now 60 degrees. We're going to see later on trig. This is one of our ones that is very common, but I'm going to ignore that fact. Okay, so here's our initial side. Again, up here is 90 degrees. So I'm going to split this up. That'd be roughly 30 degrees. And here's up another 30 degrees. So 30 degrees, 30 degrees, 30 degrees, which adds up to our 90 degrees. So our 60 degrees would be 2 of those. So that's approximately 60 degrees. Okay, well, I'll do it with the formula. We take our 60 degrees, divide by 360. The degrees would cancel, the zeros cancel. We got 6 over 36, which gives us 1/6 of a revolution. And that would be our answer. Now, once we got our angle, we got some more definitions here. We got something called an acute angle. And this is where the angle is between 0 degrees and 90 degrees. It can't be equal to 0 degrees, can't be equal to 90 degrees. Those actually have different meaning. We have something called a right angle. And you may remember right triangles from geometry. But we got a right angle. And this is when your angle is 90 degrees. We got an obtuse angle, and this is where your angle is between 90 degrees and 180 degrees. And then we got our straight angle. And this is where your angle is 180 degrees. Now let's take a look at the next problem that deals with that. It says identify the following angles as acute, right, obtuse, or straight. If the angle's none of these, then say so. You might think, well, that covers everything. 0 to 90, 90 to 180, or 180. Well, what if it's greater than 180? What if it's equal to 0? So there are some cases where that wouldn't, these definitions wouldn't apply. Okay, so 110 degrees. Well, it's not 0 to 90, it's not 90, but it is between 90 and 180. So this one would be obtuse. Now 180 degrees. Well, the one where the angle is 180 degrees is our straight angle. Uh, 25 degrees. Well, angles between 0 and 90, that's acute. And our last one, 90 degrees. When your angle's 90 degrees, then it's a right angle. So that'd be a right one. Okay. Now we got our degree breakdown. Remember, going from here up to here is 90 degrees. Well, you know, where can we draw 1 degree at? Well, I don't know. It's be pretty small as I try to draw it here. It almost appear like it's on the same line as here. So it seems like, well, it doesn't need to be any kind of finer measure than that, because I can't even hardly draw 1 degree anyway. Yeah, but remember, we're dealing in real life with computer systems that have greater accuracy. Could be you're doing something by hand where you need greater accuracy. So degrees can be broke down. And here's our breakdown. You can definitely represent degrees in decimal form. So it could be 80.235 degrees. That's one way. But there's even a finer measure. If we have 1 degree and then it's going 2 degrees, but our terminal side falls somewhere between 1 degree and 2 degrees, we have something called minutes. And there's 60 minutes is equal to 1 degree. We also have something called seconds, and this one's really easy to remember. 60 seconds is equal to 1 minute. Yeah, pretty easy, right? Now sometimes it's not so easy to remember the conversion that needs to be done. You're trying to switch something from degrees to minutes, or minutes to degrees, and so forth. You can always use your dimensional analysis to help you do the conversions if you can't remember whether you divide by 60 or you multiply by 60. For example, if I got 50 degrees, and we want to change this to minutes, so I want to convert it. Dimensional analysis always says that you're going to take what you're starting with and you put it in fraction form. So I'll put over 1. And dimensional analysis says if you have degrees right here, you're going to automatically have degrees down here. Well, we said that 1 degree is equal to 60 minutes. So I can put 1 degree, and then I'll put 60 minutes up on top here. Now minutes is represented by a single quote like that. Okay, so if I were to go through and do this, the degree marks cancel there. 1 times 1 is trivial, that drops away. So I got 50 times 60, which gives us 3,000 minutes. So it looks like going from degrees, and you want to switch everything to minutes. We're going to see we don't necessarily switch everything, but if you wanted to switch everything to minutes, then you would multiply by 60. Well, if we're going the other direction, if I was starting out with 120 minutes, and I know that's kind of confusing because that's typically like our feet measure that we're used to seeing. Well, if I want to convert from minutes to degrees, again, dimensional analysis says you always take what you're starting with, write it in fraction form. So I put it over 1. Now if minutes is up on top here, then minutes will be down below here. And we said there's 60 minutes in 1 degree, so I can put 60 minutes and then 1 degree up on top here. Well, the minutes symbol would cancel there. 120 divided by 60 is going to give us 2, and then the degree mark remains. So 120 minutes is equal to 2 degrees. Okay, now let's look at a problem dealing with this. Let me save this. And I'm going to clean up this page, and then we'll start again. Sometimes when I do the undo, sometimes when I do a new page, it crashes this tablet. But if I do a Control Z over and over, it eventually wipes out everything. Okay, so let's take a look at this problem here. We got 83 degrees, 35. Remember, this mark here is minutes. Now this is new here. We got 2. So we got 20, and this refers to seconds. So this says 83 degrees, 35 minutes, 20 seconds. And they want us to convert this, change the decimal degrees, accurate to 3 decimal places. So we want to convert this. Well, we could do the dimensional analysis to help us figure out what to do, but I could rewrite this as 83 degrees plus 35 minutes plus 20 seconds. Now this is 83 degrees plus, and to go from minutes to degrees, you're going to divide by 60. So you divide by 60, and that'll switch that to degrees. To go from seconds over to degrees, you're going to take your 20, and you're going to divide by 360. And then that'll give it to us in degrees. Well, I'm not going to sit there and try to do that by hand. Let me plug that in the calculator. So we got 83 plus 35 over 60 plus 20 divided by 3,600. And I think it said 3 decimal places. So we got 83.589 degrees. And that would be our answer. Okay. Well, to go from minutes to degrees, we talked about that, divide by 60 and so forth. But to go from seconds to degrees, let's see how in the world we would do that using dimensional analysis. Okay, so I put this over 1. Dimensional analysis says you always put this over 1, you create a fraction. And if seconds is up here, seconds has to be down here. Well, we want to eventually get to degrees, but we do know one particular measure. We know that 60 seconds is equal to 1 minute. So I'll put 60 down here. 60 seconds is equal to 1 minute. Then, since I put the minute up here, I have to put the minute down here. And I know that 60 minutes is equal to 1 degree. Now, dimensional analysis, these marks would cancel here. The seconds would cancel. The minutes would cancel here. Your only guideline is one's on top, one's on the bottom. So then I got 20 times 1, which gives us 20. And 1 times 60 is 60 times 60 is 3,600. And that's going to give it to us in minutes. Which you see, that's what I did. So to go from seconds and convert it to degrees, you divide by 3,600. Okay. Let's take a look at this on the calculator. So we're going to type this in here. Okay, so I got 83 degrees. So I'm going to do 83. And there's an angle. To get to it, we do second and then the apps. And that'll take us in the angle menu. And you see we got degrees there. And then I got 35 minutes. So I'll do 35. Go back in my angle. So do second apps. And I want to down arrow to 2 and choose it. And then I got 20 seconds. So do 20. And I don't know why, and it could be I'm missing something, but I've never been able to find seconds underneath the angle menu. If you do 2 of these little single marks here, you get an error, at least on some versions of the TA3, T84. To get to the seconds, I'm going to go into the catalog. So I'll do second, 0. Then I'm going to do an up arrow. And if you keep up arrowing, you'll find your 2 quotes. So I choose it. And now you see it looks exactly like what I input. Now if I press enter, you see we get 83.589, which is the same thing we got right here. Doing it by hand is a good technique because it really does reinforce what is a conversion between each one of these. It gives you a better understanding of minutes and seconds. Okay, let's take a look at our next problem. Number 5. And it says the change to degree, minute, second form. So it's given it to us in decimal form. Okay, so we got 43.453 degrees. Well, I can rewrite this as 43 degrees plus 0.453 degrees. What you want to do is you want to always split up the whole part separate from the decimal part. So then this is the part I'm going to work with. This is fine here, but now we want to convert this part to minutes. Well, let's think how to do that. If you ever draw blanks, like, well, do I divide by 60? Do I multiply by 60? Dimensional analysis takes that out of your hands. You don't have to think too hard on it. If I do 0.453 degrees, put over 1. Remember, dimensional analysis, you always have to throw it over 1 to create a fraction. And if degrees is up here, then degrees will be down here. And we know that there's 60 minutes in 1 degree. So I'll put 1 here for the degree, and I'll put 60 minutes up on top here. Now dimensional analysis would have us cancel those degree marks. I kind of missed it, but let me try it again. There we go. So it looks like in order to convert this to minutes, we have to multiply by 60. So here, there's the train again. I guess I won't pause this. So I'm going to take my 0.453 and I'm going to multiply it by 60. And that's going to give it to us in minutes. So we got 43 degrees plus 0.453 times 60. So 0.453 times 60. And we get 27.18. And this is in minutes. Well, remember up here where we split the whole part separate from the decimal part, that's what we're going to do down here. So this is 43 degrees plus 27 minutes plus 0.18 minutes. The part we're working with now is this last piece right here. We want to convert that to seconds. Now again, if I draw a blank, dimensional analysis always guides you exactly what to do in conversions. So that's a neat part of it. We take the 0.18 minutes, put over 1, times, then we got another fraction. If minutes is up here, then minutes will be down here. And then degree, or seconds, will be up here. Well, we know that 60 seconds is equal to 1 minute. Well, these minutes would cancel here. So it looks like to go from minutes to seconds, we're going to multiply by 60. And that kind of makes sense if you think of it in terms of our time measurement. So this would be 43 degrees plus 27 minutes plus, and then I'll take 0.18 times 60, and that's going to change that to seconds. So we got 43 degrees plus 27 minutes plus 0.18 times 60, and we get 10.8 seconds. Do you leave the decimal there? Probably depends upon your application. Most times you don't see decimals written in these, but so our answer would be 43 degrees, 27 minutes, and I'd round it to 11 seconds. Because remember I said that by hand we probably couldn't draw a degree anyway. Well, minutes splits that 1 degree into 60 parts. So, and then each one of those is a minute, and each one of those is then split into 60 parts, which are seconds. So all of a sudden, we got a very fine measure at that point. That's why oftentimes you don't need to keep this decimal. But again, it depends upon your application in terms of, you know, what kind of precision do you need. Let's look at this on the calculator. Okay. We got 40, oops, try it again. 43.453. And I'm going to go into my angle here. Now choose degrees. So we got this in degrees. We want to convert this to degrees, minutes, and seconds. Well, I go back into my angle. And then I want to choose number 4, DMS, degrees, minutes, seconds. And the little arrow in front of it means we're converting that to that form. So then I press enter on that, and I press enter again. And I guess I didn't need to put the degrees on there. Okay, let's try that again. 43.453, and now let me do the angle and choose, I'll choose 4, choose it, and press enter. Interesting. I thought you had to put the degrees on that, but obviously that doesn't work. But I'm real curious about why it doesn't work. But anyway, you see we got 43 degrees, 27 minutes, and then 10.8 seconds. Obviously it doesn't round it for you. Now if I go to mode, you're going to see a bunch of different options. Here you see I got radian and degree. And I really thought, since my calculator by default was in radian, which we'll talk about later on, that I needed to actually put the degree mark there, but I was obviously wrong. So this must assume that it's already in degree when you do it. If you put degrees there, then it gives you the wrong result. Anyway, ignore my first entry there, and the second entry is how you use the calculator for it. Okay, let me let's see if there's another one similar to that. Okay, let's take a look at this one, and then I'll save the page. It's telling us this is the Greek symbol for alpha. It's telling us alpha is 37 degrees, 15 minutes, and 23 seconds. And beta, extra B with a line, and it's kind of curved like that, I don't draw them real well, is 37.237 degrees. And it's asking us to identify whether alpha is less than, equal to, or greater than beta. Excuse me. Well, easiest way is probably to use a calculator on this, but we could do it by hand. I'm going to do it by hand just so we see that, another example of that. we want to convert this to decimal form, so we're going to take our 37 degrees, and I'll put a plus in between these, because that's what's implied. It means we got 37 degrees plus 15 minutes plus 23 seconds. We want to convert these to degrees, so I'm going to take my minutes, which is 15, and divide by 60, and that'll convert that to degrees. And here I'll take my seconds, which is 23, and divided by 3600, and that'll convert that to minutes. So if I do those fractions in my calculator now, I got 37 plus 15 over 60 plus 23 divided by 3600, and then equals. And I'll take it 3 decimal places, because that's what the other one is. This gives us 37.256. Well, this is what alpha is, and here's what beta is. So it appears like alpha is greater than. So our answer on this one is alpha is greater than beta. Now again, we could use our calculator to convert that to decimal form. So if we go to 37 degrees, so I'll do my second apps to go in an angle, choose degrees, and I got 15 minutes, so do 15 going back in my angle, and choose minutes. And then I got 23, and it could be the seconds is somewhere on here, but I'm going to go in my catalog, so I do second 0, and I'll go up to seconds and press enter, and then I'll simply press enter again. And you see we get 37.256, which is what we got there. Okay, let me save this. And now let me wipe out this. Doing a Control Z will clean out the page. Okay, now the next part deals with some basic formulas with circles. So let's talk about this. Our circle, well, looks like this. And remember when we were dealing with angles, we started our initial side, we went all the way around, came back to our initial side, then that was 360 degrees. So you'll find that going all the way around is going to be 360 degrees. Because we could put some kind of coordinate system on our circle here and start this as our initial side. So that's our initial side. So then going all the way around would be the same as 360 degrees. Well, we have something called a semicircle. And I was drawing a blank on this morning, so I had to Google this. A semicircle is just half a circle. So it'd look like this. Well, remember, if I start here and I go over to here, how many degrees is that? It's 180 degrees, isn't it? So we need to keep that in mind. Now for a circle, it has an area associated with it. Remember, your area is pi r squared. R is your radius. That's the distance from your center here out to the edge. We also have circumference, which is 2 pi r. Or another formula for circumference, 2 times r is your diameter. So we could have pi d, where d is your diameter. Now if you got a semicircle, your area would be half as much. So your area would be 1/2 of pi r squared. And your circumference, if the circumference, remember, is the distance around, you can think of it as the perimeter of your circle. It's just got a different name. Our circumference is 2 pi r, so if I just got a half a circle, then my distance going here, excluding that there's no piece right here, my distance around the perimeter, would be 1/2 times 2 pi r. The 1/2 times 2 would cancel, and we'd have pi r. Different variations you could have of that, but those are the ones we'll be working with. Okay, so let's take a look at number 7. It says find the following, round 2 decimal places, circumference of a circle that has radius 20. So telling us r is equal to 20, and they want us to find the circumference. Well, I come over here and I'm looking for some kind of formula that ties these together, and specifically they're saying circle, which means we're going to be working with these formulas. Well, we're trying to find a circumference. The first formula here for area doesn't even have circumference, so we have to use this. And since we're given r instead of d, we probably want to use this formula. So circumference is equal to 2 pi r, and they told us that r is 20. Did I put a unit measure on that? I guess I didn't. It's pretty vague, but so then circumference 2 times 20 gives us 40 pi. And they want us to round to 2 decimal places. So I'll go put this in my calculator. So I got 40, and I want to access pi. Pi is above your caret, so we're going to do second and then the caret, and then you can press enter. So the circumference is going to equal to 125.66. No memory. Was it 2 decimal places? Yeah, 2 decimal places. So that would be our answer. Let me grab a drink here. Getting parched. Okay, number 8. Same instructions, find the following. Radius of a circle that has circumference 30. So they're telling us circumference is 30, and we're trying to find r. Well, I'm going to go back to the same formula. And we're dealing with a circle, so we're dealing with these formulas. So we're going to have c is equal to 2 pi r. They tell us c is 30, so put 30 in there, and we got 2 pi r. We want to get r by itself, so we're going to divide both sides by 2 pi. And when we do that, these 2's cancel, the pi's cancel. And since we're wanting it rounded 2 decimal places, that I could simplify this fraction and have 15 over pi. That'd be an exact answer, but they're wanting it rounded. So 30 divided by 2 pi. So I'll do 30 divided by, if you ever have more than a single number, single pi, on top or bottom of your fraction, you have to put parentheses on it. So I'll put beginning parentheses, then 2 pi, second caret is again pi, and then closing parentheses, and then press enter. And we get 4.77. And that would be our answer. Now if I didn't put the parentheses there, if I did 30 divided by 2 pi, enter, see how we get the wrong answer. So be careful on that. If you got more than a single number, single pi on your top or bottom of your fraction, numerator, denominator, make sure you put parentheses around it. Okay, the next one is one I actually had to look up the definition of semicircle. As I get older, I forget things. This is asking us to find diameter that has an arc length of 5. Now when we say arc length of 5, they're saying that this distance here is 5. Well, we'll come back to that. But this all the way across here would be our diameter. Your diameter is the distance all the way across the circle. A semicircle is half a circle. So if I were to continue this circle, not that I can draw it very good, but this side here should be symmetric with this side. If this distance here is 5, then this distance down here should also be 5. Now remember, your circumference is the distance all the way around. So the distance all the way around is 5 plus 5, or 10. So really they're telling us the circumference is 10, and they're wanting us to find D. Well, if I consider the entire circle, I could try to use the formulas over here and do it. It gets a little bit trickier though, because we're so ingrained into thinking circles. If I come over here, I want to use the formula C is equal to pi d. So C is equal to pi d. Well, C we said was 10 equals pi d. And then to solve for d, I'm going to divide both sides by pi. So I got 10 divided by pi is equal to pi d divided by pi. Pi's cancel. We got d is equal to 10 over pi. And again, we're on that to 2 decimal places. So we got 10 divided by, and then second caret for the pi, and enter. And we got 3.18. And that would be our answer. Now the next problems, let me get over to them. I want to show the picture, and I'm going to talk about how the formula is derived for this. But we got a circle here. Now this S represents this length of this arc. The C represents the distance all the way around. That's our circumference. Now don't think that the C here just represents this side here. C represents the distance all the way around the circle. Angle that it opens up is theta. And then the distance from the center to the outer edge is always R. So that's a formula we're going to work with. And on these next problems, they're going to give us different pieces of this, and they're going to ask us to find the missing variable. C, of course, is our circumference. Theta is our angle it opens up. S is the distance of that arc, and then R is the radius. Okay. Well, if we take a look at the proportion, got a circle here. I showed you the first picture because I can't draw circles very well. So refer to this if you need to see a good picture. We said this angle here is theta. We said the circumference is all the way around. We said this distance here is S, the length of that arc. Now I'm going to put the angle theta in terms of the angle, the distance all the way around, which is 360 degrees. And then I can set that equal to, proportion-wise. Now here we're talking about this distance is angle, so we're going to put the distance of this arc. So I'll put S up on top here. And then over 360 degrees all the way around, and circumference is all the way around. So we're going to put our circumference down here. So our proportion that we can use on these is theta over 360 degrees is equal to S over C. I don't draw S's very well. So let me try to do that again just to see if I can make it look a little bit better. It's probably as good as I'm going to get. But that would be our formula. So for these next problems, we're going to use that formula to help find the missing variable. So let me scroll down a little bit here and take a look at number 10. They tell us S is 14 centimeters. They tell us circumference is 210 centimeters. And they're wanting to know what theta is. Well, let's plug in what we given in our formula. So we got theta over 360 degrees is equal to S, which is 14 centimeters, over C, which is 210 centimeters. Okay, well, the centimeter is going to cancel there. And I'm trying to get theta by itself, so I'm going to multiply both sides by 360 degrees. So take 360 degrees times theta over 360 degrees, and then 360 degrees times 14 over 210. Now over here, the 360 degrees will cancel, and we got theta equals, I'm just going to plug this in the calculator. So I got 360 times 14 divided by 210, enter, and that tells us that theta is going to equal to 24 degrees. And that's our answer. Okay. Take a look at another example. Number 11. Telling us that C is equal to 500 feet. Theta is, oh well, I guess it doesn't matter. I really didn't plan it that way. I just made these numbers up, so it's kind of strange that this come up as 24 degrees and this one is 24 degrees, but oh well. And then we want to know what S is. Again, we're going back to our formula. So we got theta over 360 degrees is equal to S over C. Theta is 24 degrees. S we don't know. And C is equal to 500 feet. Well, first off, these degrees will cancel because they're one's on top, one's on the bottom. And I can multiply both sides by 500 feet to get the S by itself. So we'll take 500 feet times 24 over 360 is equal to S over 500 feet times 500 feet. So those are going to cancel. And I'm going to plug this in. Probably won't come out nice, I'm assuming. Let's see, 500 times 24 divided by 360. Enter, and we get, I'll take it 2 decimal places, I guess. We got 33.33 feet. Doesn't say how many decimal places, just take it to 2 decimal places. Precision all depends upon the application you're dealing with. So if you're doing road construction, 33.33 feet is plenty precision in most cases. But if you're designing some kind of component for a computer or something, you may need to take it out to more decimal places. Let me save that. I think that's saved. Let me try it again. Yeah, it saved it. Okay. Now let me clean out that page. Eventually get there. Okay. Now let's look at our next problem. Here we got S. This is number 12, I guess. We got S is equal to 20 feet. Theta is equal to 35 degrees. And we want to know what our circumference is. Now remember the formula we're dealing with is we got theta over 360 degrees is equal to S over C. So we're going to plug in. Our theta is 35 degrees, so put 35 degrees in for theta. Over 360, S is 20 feet over C. If you remember proportions, the nice part about proportions is, proportion is when you got a single fraction equal to a single fraction, is you can cross multiply. When I say cross multiply, we're going to take 35 degrees times c. So we got 35 degrees c. And then we'll take 360 degrees times 20 feet. So we'll have 360 degrees times 20 feet. Now notice how I've kept the units of measure here, just because I want to demonstrate it. You could also cancel the degrees right here. I'm trying to get c by itself, so I'm going to divide both sides by 35 degrees. And we got 360 degrees, 20 feet over 35 degrees. Nice part about units of measure is if you keep them in the problem and you keep your mathematical principles correct, they'll cancel each other out, and then it'll give you the appropriate measure at the end. This degrees here cancels this degrees. So then our circumference, I'm going to do this in the calculator, 360 times 20. Even though I don't need it based upon how the calculator is designed, I'll go with my rule I told you earlier. If you ever have more than a single number or single pi on top or bottom, put parentheses around it. So we got 360 times 20, closing parentheses, divided by 35. And then press enter. Now take it 2 decimal places. So our circumference will be 205.71 feet, because that's what we have left there. So that'll be our answer. Okay, so let's take a look at this one. We got S is equal to 500 centimeters. Theta is equal to 15 degrees. And we're wondering what R is. Well, we got our formula. Theta over 360 degrees is equal to S over C. So we got given S, we're given theta, we're given C. We want R. Well, remember what C is equal to. C is equal to, or circumference, is equal to 2 pi R. So what I could do is modify this formula slightly. Instead of having C down there, I'll put 2 pi R. And now it's going to make a little bit more sense, because that's what we're looking for is R. So let's plug in everything now. Theta is 15 degrees over 360 degrees is equal to S, which was 500 centimeters, over 2 pi R. Now I'm going to do a little bit of simplifying. These degrees are going to cancel, so those are gone. And remember, we have a proportion here. We got a single fraction equal to a single fraction, so we can cross multiply. So we're going to have 15 times 2 pi R. So 15 times 2 pi R is equal to 360 times 500 centimeters. Now 15 times 2 is 30, so we're going to have 30 pi R is equal to, let me go ahead and plug that in, 360 times 500, 180,000. So 180,000 centimeters. Now we're trying to get R by itself, so we're going to divide both sides by what's in front of our R. So we're going to divide both sides by 30 pi. And over on the left side, the 30s will cancel, the pi's will cancel, so we're left with R. And over on the right side, I'm going to plug that in my calculator. I have to be careful though, because we have more than a single number or a single pi down in the denominator, so we have to put parentheses on that part. So I'll do 180,000 divided by beginning parentheses, and then I got 30 pi. So 30 and then second caret for the pi, and then closing parentheses and then enter. Now I'll take it 2 decimal places, but R is equal to 1,909.86 centimeters. because remember, your unit measure just carries down. Okay, now that was our proportion dealing with the arc length. We can also have a proportion dealing with the area, and I'll show you the picture here, and then I'll try to draw it myself. Okay, so this is our picture. We got a circle, of course. We got our arc length here. We got our angle. The capital uppercase A represents the area of this little piece here. The R, of course, is our radius. Well, so let me draw that. Again, look at that picture for a good picture. This of course is S. A is our area of this piece right here, and then this will be theta. I didn't draw it big enough, but so we're going to create a proportion. So we're going to take the area of this piece right here over the area of the entire circle. Well, area of a circle is pi r squared. So we get pi r A over pi r squared. And you notice that's what we came up with on this first piece here. Now we're putting it in specifically in terms in relation to pi or theta, our angle. So if A represents the area of this segment, then, and that's on top, then theta, which represents just the angle right there, should be up on top. Now the angle all the way around is 360 degrees, which is where they get this formula here. Okay. So 14 tells us R is equal to 20 centimeters. And, oops, let's try it again. Theta is 42 degrees. And they're wanting to know what A is equal to. Well, not exciting. We're just plugging them in this formula. So we got A over pi r squared. So I'll put 20 centimeters in here, squared, equals theta, which is 42 degrees, divided by 360 degrees. Now we want to solve for A. First off, here we got pi. Now we got 20 in centimeters in here squared. These you can think of centimeters like a variable. So we got like 20 times a variable. When you got multiple items inside your parentheses connected by multiplication and you raise it to a power, you can take everything to that power. So we'll take the 20 to the second power, and we'll take the centimeters to the second power. So we're going to have 20 squared, and we'll have centimeters squared. You really do treat your units of measure just like a variable when you're working with these formulas. Now over here, these degrees will cancel. So we've got 42 over 360. I could even simplify that further, but I'm not going to bother. Because I'm putting my calculator in a few minutes anyway. Now 20 squared will be, what was that, 400 pi centimeter squared equals 42 over 360. We're trying to get A by itself, so I'm going to multiply both sides by 400 pi centimeter squared. So multiply that. And we'll also multiply this side by 400 pi centimeter squared. Now over here, the 400s cancel, the pi's cancel, the centimeters squared cancel. And we're left with area. And I'm going to go ahead and plug that in the calculator because I think they're wanting, it doesn't say. If I were to leave it an exact value, I wouldn't want to actually multiply it times pi. So let me just do the numbers first. So I got 42 over 360 times 400. And then enter. Now we get a decimal. Remember on your TA3, TA4, if you do a math, enter, that'll change it to a fraction. So the exact answer is 140 over 3 pi centimeters squared. Well, if I want to get approximation, 140 over 3, I just simply do a times and then pi. So do second caret, and then press enter. Now I'll take it 2 decimal places. This would be 146.61 centimeters squared. Now we know that area is supposed to be in terms of something squared, like feet squared, inches squared, centimeters squared. By leaving the units of measure and making sure everything was mathematically correct, it told us what the unit of measure was going to be. So that's kind of the neat part about working those. Do have to be careful though. Okay, one more of those. We got R is equal to 15.6 centimeters. A is equal to 250 centimeters squared. And we want to know what theta is. Well, we're going to go back to our formula. Oops, over here. So we got A, which is 250 centimeters squared, over pi r squared. So I'm going to have pi times r, which was 15.6 centimeters squared, is going to equal to theta. Theta was what we're trying to find, over 360 degrees. Okay, so we got 250 centimeters squared, then pi times 15.6 squared. Because remember, we square the 15.6 and we're going to square the centimeters. So 15.6 squared. And we get 243.36. Now when I square the centimeters here, then this becomes centimeters squared. Well, notice we have centimeters squared here and centimeters squared here, so those are going to cancel. And I'm trying to get theta by itself, so I'm going to multiply both sides by 360. And since I'm kind of running out of room, I won't show that. But we're multiplying both sides by 360. So I got 250 here over 243.36 pi equals theta. Okay, well, maybe kind of tricky to plug in your calculator, but I'm going to do 360 times, and then I got 250. There's just a single number on top of the fraction, so I don't need to put parentheses around it. Divided by, and then I'll put a beginning parentheses because we got a number and a pi down here, so you have to have parentheses around that. And then 243.36 pi, so we'll do second caret, and then closing parentheses, and then enter. And so then theta is going to equal to 2 decimal places, would be 117.72 degrees. Again, keeping the units of measure in there causes these to cancel away, and then we're just left with degrees, which is what our answer should be represented in. Well, in this lesson, we took a look at angles, degrees, and arcs.